Welcome back to the Deep Insight Dialogue.
Great to be here.
Today we're cutting through the noise, really trying to get to the heart of something big. We've got Andriy Burkov's the 100-page machine learning book.
That's right.
And our goal, as always, is to give you a clear, concise, sort of actionable understanding of these, well, complex ideas, helping you connect the dots without getting totally bogged down.
Indeed. And it's a fascinating book. It has this unique read first, buy later idea behind it.
Oh, interesting.
Yeah. And it really aims to demystify machine learning, make it accessible. So our mission today is to go maybe even a step further.
Okay.
Translate its core concepts into really clear, digestible insights, especially for anyone who's just curious about how these, intelligent systems actually learn. We want to make it understandable, really, no matter your technical background.
Perfect. Because before we dive in, let's just tackle the name itself. Machine learning. It sounds so futuristic, doesn't it?
It does.
But what does it actually mean? Is it just a fancy term for a smart computer program?
Yeah.
One that follows a really long list of instructions?
That's a really good question to start with. And the book actually kicks off with a neat historical bit.
Oh, yeah.
Yeah, the term coined way back, 1959, Arthur Samuel at IBM.
Wow, 1959.
Yeah. And, a bit like some modern tech buzzwords, it was partly a marketing thing back then.
Really? Marketing?
Sure, to attract clients, attract talent, to this new burgeoning field. But, and this is the key thing, it's definitely more than just marketing. The real difference is how learning works for a machine compared to, say, a traditional program.
Okay.
Think about it like this. Imagine you learn to play a video game, right?
Okay, yeah.
If someone, tilted the screen slightly, you could probably still play. You'd adapt.
Sure, yeah, I'd adjust.
Right. But a traditional computer program, if it was only ever trained on a perfectly straight screen, it would likely just fail completely if the screen was rotated.
Because it only knows that one specific view.
Exactly. It was only programmed for that one scenario. It can adapt. It just follows its fixed instructions. Machine learning, though, it aims for something different, something called generalization.
Generalization, okay.
It means it tries to adapt to slight changes, distortions, or even totally new inputs it's never seen before.
How?
Well, it aims to recognize the underlying patterns and relationships in the data. It's not just memorizing specific examples or following rigid rules.
Okay. So it learns the concept, not just the specifics.
Precisely. So if a machine learning algorithm learned the game on a straight screen, ideally it could still play if the screen was rotated a bit, because it learned the idea of the game, the patterns, not just exact pixel locations.
That makes sense.
That ability to adapt, to handle variations without being explicitly told how to handle every single one, that's really the heart of machine learning.
Okay, so let's unpack this a bit more. It's really about adaptability, isn't it? Not just executing code line by line. The machine isn't just following orders. It's building some kind of deeper understanding, maybe, that lets it work even when things change slightly. It's actually learning.
That's a great way to put it.
Okay, fantastic starting point for our Deep Insight Dialogue today. Right, so the book apparently breaks down machine learning into 4 main types, like different teaching styles for machines.
That's a perfect analogy, yeah. 4 main pedagogical approaches, you could say.
Okay. Can you walk us through them, maybe with some simple examples so we can really get our heads around how these different methods work?
Absolutely. Think of them as distinct training regimes, each really suited for a particular kind of problem or a specific type of data.
Got it.
Okay, first up, we have supervised learning. This is probably the most common type you'll encounter in practice.
Okay, supervised.
It's like learning with a very patient teacher. Imagine they give you a quiz, but then immediately give you all the correct answers.
Okay. Learning with the answers provided.
Exactly. You feed the machine what are called labeled examples. These are basically pairs. You give it an input, and you give it the correct output, the right answer, the label.
Input and correct answer. Got it.
And the machine's job is to learn the mapping, to figure out how to predict that correct output for new, unseen inputs based on all the examples it studied. The classic example, which the source uses, is spam detection.
Right. We all know spam filters.
So you give the machine, say, thousands of emails, and for each email, you've already marked it clearly, Spam or not spam.
So the email is the input and spam, not spam, is the label.
Precisely. The machine studies these labeled examples, looking for subtle patterns inside the emails, words, senders, formatting, whatever, that correlate strongly with the spam label. It keeps learning until it can make a pretty good guess about whether a brand new email, one it's never seen, is spam or not.
Okay, makes sense.
And the book introduces a couple of key terms here you might hear. The input example, like an email, that's converted into a feature vector.
Feature vector sounds technical.
It just means a numerical fingerprint, a list of descriptive numbers. For an email, features might be numbers representing things like, does it contain the word Viagra? Maybe 1 if yes, 0 if no. Is the sender in your contacts, 1 or 0? How many exclamation marks? Just the count.
Oh, okay, so turning the email into numbers.
Exactly. Each number is a feature, and the label, as we said, is just the correct answer you want it to learn, like spam or not spam.
Okay, supervised learning. Got it. What's next?
Next up is unsupervised learning. Now, this is quite different.
How so?
Because here, there's no teacher, no labels, no correct answers provided.
No answers. So what does it learn?
It learns structure. You give the machine a data set that's just a collection of unlabeled examples. Its job is to try and find patterns or structures or relationships within that data all on its own.
Like sorting things out.
Exactly. It's like giving a kid a big pile of mixed Lego bricks, different colors, different shapes, and just asking them to sort them into groups without telling them what the groups should be.
They just figure it out based on similarity.
Right. They identify similarities, maybe group by color or by shape, and organize them. The machine does something similar with data.
Okay, so what are some examples?
Well, it might automatically group customers with similar buying habits, or identify different types of galaxies in astronomical images without astronomers having predefined those types. This task is usually called clustering.
Clustering. Finding groups.
Yep. Unsupervised learning is also used for something called dimensionality reduction.
Reducing dimensions.
Yeah, basically simplifying complex data. Making the feature vector shorter by finding the most important features and getting rid of less useful ones while still keeping the core information.
Okay, why do that?
Helps with visualization or sometimes makes it easier for other algorithms to learn. It's also used for outlier detection, spotting weird or unusual data points that don't fit the main patterns, like finding potentially fraudulent credit card transactions.
Finding the odd one out. Makes sense. So that's unsupervised. What else?
Then there's semi-supervised learning. And as the name kind of suggests, this is a mix, a blend of the first two.
Supervised and unsupervised mixed together.
Sort of. You have a small amount of labeled data where you know the answers, but then a much larger amount of unlabeled data.
Okay, why? What's the goal?
The goal is usually the same as supervised learning. Build a model to predict labels for new inputs. But the clever part is that the huge amount of unlabeled data can actually help the algorithm find a better model, even though most of it doesn't have answers.
How does that work? Adding data without answers helps.
It seems counterintuitive, right? But the unlabeled data gives the algorithm a much better picture of the overall landscape or the distribution of the data. It shows where the dense regions are, how things are generally structured. A smart algorithm can use that structural information from the unlabeled data to make more informed decisions about where to draw boundaries or make predictions, even with only a few labeled examples to guide it.
Huh. So the unlabeled stuff provides context.
Exactly. It helps fill in the gaps.
Okay. And the last one?
The last one is reinforcement learning. And this is a fundamentally different beast altogether.
How so?
It's often compared to training a pet, maybe a dog, with treats.
Okay, positive reinforcement.
Yeah. Imagine the machine, or an agent as it's called, living inside an environment. This could be a video game, or it could be controlling a real robot, or managing resources in a simulation.
Right.
The agent performs actions within this environment. And for each action, it gets a reward if it did something good, or maybe a penalty if it did something bad.
Carrot and stick approach?
Pretty much. The machine's ultimate goal is to learn a policy. A policy is basically a strategy, a set of rules that tells it the best action to take in any given situation to maximize its total long-term reward. Not just the immediate reward, but the sum of rewards over time.
Okay, so it learns by trial and error, figuring out what leads to the best outcomes.
Exactly. It explores, tries things out, sees what works. This powers things like game-playing AIs, think AlphaGo beating human champions and robotics, autonomous driving, complex resource management. The book we're looking at mentions it focuses mainly on other types, but reinforcement learning is a huge and really exciting area.
Okay, wow. So quick recap. Supervised is learning with answers. Unsupervised is finding hidden patterns alone. Semi-supervised is a mix, using unlabeled data for context. And reinforcement is learning from rewards and punishments, like training a dog.
You got it. That's a great summary of the four main branches.
That framing makes so much intuitive sense. Okay, since you said supervised learn is the most common, let's really dig back into that spam detector example from the book. Because you said it gives a fantastic picture of how a machine actually goes from reading an email message to deciding, yep, this is spam. How does that transformation actually happen from, words on a screen to a decision?
Right. This is where the clever engineering comes in. It's a process with a few crucial steps. It's all about converting something a human understands easily, like an email, into something a machine can process, which is basically just numbers.
Numbers of the machine's language.
Exactly. So first step, gathering data. For our spam detector, this means someone has to collect a lot of emails, let's say 10,000 emails. And crucially, a human has to go through and manually label each one as either spam or not spam.
Wow, 10,000 emails manually. That sounds like work.
It is. This collection of labeled emails is your training data. It's the textbook the machine learns from.
Okay, step 1, get the labeled examples.
Step 2, converting to feature vectors. Remember, machines need numbers, not text. So a data analyst, or maybe a data scientist, has to figure out how to turn each email into that numerical feature vector we talked about, that list of numbers describing the email.
Right, the numerical fingerprint.
Yeah. And a super common technique for text is called bag of words.
Bag of words, like just throwing all the words in a bag.
Kind of. Imagine you create a dictionary of, say, the 20,000 most common English words.
Okay, a big dictionary.
Right. Then for each email, you create a list, a vector, that's 20,000 numbers long. The first number corresponds to the first word in the dictionary, maybe the word A. If the email contains A, that first number is 1. If not, it's 0.
Okay.
You do this for the second word, maybe aardvark, all the way down to the 20,000th word, maybe Zulu. If the email contains Viagra, maybe that's the 18,500th word, then the 18,500th number in the list is 1, otherwise 0.
So each email becomes this huge list of zeros and ones.
Pretty much. A long, sparse, mostly zeros list, but it's a numerical representation of the email's content. That's the feature vector.
Okay, that makes sense. Tedious, but logical. What's next?
Next, you have to convert the labels themselves into numbers too. Spam and not spam aren't numbers. For many algorithms, you might just use 0 for not spam and 1 for spam. Simple enough. But the specific algorithm the book uses to illustrate this, called a support vector machine, or SVM, it actually prefers using -1 for not spam and +1 for spam.
-1 and +1. Any reason why?
It just works out nicely with the underlying math of the SVM algorithm. So now, for each of our 10,000 emails, we have two things. A very long numerical feature vector, the bag of words, and a single numerical label, +1 or -1.
Okay, data prepped. Now the learning.
Now the learning. This is where the learning algorithm, the SVM, comes in. The SVM essentially visualizes each of these feature vectors, each email, as a single point in a vast imaginary mathematical space.
A 20,000 dimensional space. Hard to picture.
Impossible for us to visualize, yeah. But mathematically, it's just a location defined by 20,000 coordinates. And the really ingenious goal of the SVM is to draw an invisible boundary, or maybe think of it as a wall, in this incredibly high-dimensional space.
A wall separating what?
Separating the spam points, the ones labeled +1, from the not spam points, the ones labeled -1. The separating wall is technically called a hyperplane, but wall or boundary works fine. It's the decision boundary.
Okay, so it finds a line, well, a wall, to divide the two groups.
Yes, but not just any wall. The SVM algorithm specifically searches for the wall that separates the two groups with the largest possible margin.
Margin, like a safety zone.
Exactly like that. The margin is the empty space, the gap, between the wall itself and the closest data points from each class. The SVM wants to maximize this gap, push the wall as far away from both the spam examples and the not spam examples as possible.
Why is that important? Why the biggest gap?
Because that largest margin is key to generalization. It makes the model more robust, it gives it more breathing room so that when a new email comes along, even if it's slightly different from the training examples, it's still likely to fall on the correct side of the boundary. It builds in a buffer against small variations.
Okay. So maximizing the margin helps it work better on unseen data.
Precisely. Once the algorithm finds this optimal wall with the maximum margin, that wall is your trained model. It's stored as a set of mathematical parameters.
And making a prediction.
To make a prediction for a new email, one you haven't seen before. You first convert that new email into its numerical feature vector using the same bag of words process. Then you basically plug those numbers into the model's equation, which represents that wall. The equation tells you which side of the wall the new point falls on. The +1 side, predict spam, or the -1 side, predict not spam.
Wow. Okay, that's a really clear picture now. So why does this matter to you, our listener? Well, it means when you click that Mark as Spam button in your email client.
You're doing more than just cleaning your inbox.
Exactly. You're actually providing a crucial piece of labeled data. You're giving the algorithm another example, another point in that high-dimensional space, helping it refine where that boundary should be.
The more good examples it sees, the better it gets at drawing that invisible wall.
Which means fewer spam emails making it through, and hopefully fewer important emails getting lost in the spam folder. It's a direct link between user feedback and the model improving.
It absolutely is. That human labeling is often critical. #TaxHack 1.3, why models work on new data, generalization.
That spam example really brings it home.
Yeah.
But it also leads to maybe the most fundamental question. Why does a model trained on old data actually work for new data it's never ever seen before? You call this generalization, right?
That's right. Generalization. It's the holy grail, really. If a model only worked on data it had already seen, it wouldn't be very useful.
So how does it manage to work on new stuff?
Well, intuitively, it relies on a key assumption, that the future will be somewhat similar to the past. If your training examples, those thousands of spam and not spam emails were chosen well, if they're truly representative of the kinds of emails people generally receive.
If they cover the typical patterns.
Exactly. Then new emails of the same type, new spam or new legitimate emails, they will likely fall close to the clusters of existing examples in that high-dimensional space we talked about.
Okay, so new spam emails will probably land near the old spam emails on that imaginary map.
Statistically, yes. They'll share similar features, similar bag of words vectors. The same goes for new legitimate emails. They'll likely land near the other legitimate emails.
Right.
Now, because the decision boundary, especially one like the SVMs, that deliberately tries to maximize the margin, is drawn to broadly separate these clusters.
Not just individual points, but the whole groups.
Right. It's positioned to best separate the bulk of the spam from the bulk of the not spam. Therefore, it will still, with high probability, separate the new examples correctly because they land within those clusters.
So it's playing the odds based on the patterns in the training data.
Exactly. Errors will still happen, of course. Some new emails might be unusual, they might fall close to the boundary, or even on the wrong side. But if the training data was good and representative, the number of correct predictions on new data should significantly outweigh the errors.
And the book emphasizes the size of the training set matters here.
Absolutely. The larger and more diverse your training set, the better it represents reality, and the more likely it is that new examples will be similar to something the model has already learned from.
More data smooths things out.
It helps capture the true distribution. And specifically for the SVM, that pursuit of the largest margin is explicitly designed to make it less sensitive to the exact position of individual training points. By pushing the boundary as far away as possible from all existing examples, it increases the model's confidence when it encounters slightly different new data. It's building in robustness for the future.
It's optimizing for future performance, not just memorizing the past.
That's the goal of generalization.
Okay, so we've got a good handle on supervised learning for classifications, sorting things into buckets like spam or not spam, using things like SVMs. But what if you don't want a category? What if you want to predict an actual number, like how much a house will sell for, or maybe forecasting next month's sales figures based on, say, ad spending?
Right. That's a different type of supervised learning task called regression. And one of the foundational algorithms for that is linear regression.
Linear regression. The name sounds pretty straightforward, like drawing a line.
It is. That's exactly the intuition. Linear regression is used when your goal is to predict a continuous numerical value, not a category. Think house prices, temperature forecasts, sales figures, stock prices, anything where the answer is a number on a scale.
Gotcha.
The example from the source material is a classic one, predicting a company's annual sales based on how much money it spends on radio advertising.
Okay, so more radio ads equals more sales, maybe?
That's the potential relationship you want the model to find. Imagine you have data from many companies. You plot radio ad spending on the horizontal axis X and their annual sales on the vertical axis Y. You'd get a scatter plot, a cloud of dots. each dot representing one company.
Right.
The core idea of linear regression is to find the single straight line of best fit that goes through that cloud of dots. Or if you have multiple input features like radio spending and TV spending and newspaper spending, then instead of a line, it finds the best plane or even a hyperplane in higher dimensions.
But always flat, like a line or a plane.
Yes, that's the linear part. It assumes a linear relationship between the inputs and the output. The goal is to find the specific line or plane that lies as close as possible to all your training data points.
How does it measure close?
Typically, it minimizes the squared error. For each company in your training data, it calculates the vertical distance between the actual sales data point and the point predicted by the line. It squares that distance, that error, and then it sums up all those square distances for all the companies.
Squaring the error. Why do that? Why not just the distance?
Squaring does two useful things. First, it makes all errors positive, so they don't cancel each other out. Second, and more importantly, it heavily penalizes large errors. A point far from the line contributes much more to the total sum of squares than a point that's only slightly off.
So it really pushes the line to avoid big mistakes.
Exactly. It encourages the line to fit the bulk of the data well and tries hard to bring those outliers closer. The algorithm adjusts the slope and intercept of the line until it finds the combination that makes that total sum of squared errors as small as possible.
Okay, so find the straight line that best captures the trend, minimizing those squared misses. And you mentioned earlier, the book notes this tends to not overfit as much. Can you remind us what overfit means again and why linear regression is less prone to it?
Right, overfitting. That's when a model learns the training data too perfectly. It essentially memorizes the training set, including all the random noise and little quirks that are only present in that specific set of data.
Like the student memorizing answers for one test.
Precisely. The problem is when you show this overfitted model new data it hasn't seen before, it often performs poorly because those specific quirks aren't there anymore and it hasn't learned the true underlying pattern well enough.
That's brittle.
Exactly. Now, linear models, because they are inherently simple, they can only draw straight lines or flat planes. They're generally less flexible. They can't twist and turn to perfectly hit every single noisy data point in the training set.
Their simplicity restricts them.
Yes, and that restriction is often a good thing. It forces the model to capture the main overall trend in the data rather than getting distracted by the noise. This inherent simplicity makes them less prone to overfitting and often helps them generalize better to new unseen data compared to more complex models.
Okay, linear regression for numbers. Got it. Now this next one. The name is really tricky, logistic regression. It sounds like it should also predict numbers like linear regression did, but the book flat out says it's a classification algorithm. What's going on there? That name feels like a deliberate attempt to confuse us.
Yes, it's probably one of the most confusingly named algorithms out there. It catches everyone at first. The regression part of the name purely comes from its mathematical mechanics, which are very similar under the hood to linear regression. It also works by calculating a weighted sum of the input features, finding a kind of lineal boundary.
Okay, so the math looks like regression.
Right, but its purpose, its output, is absolutely for classification. Specifically, it's designed for binary classification, predicting one of two possible outcomes. Yes or no, spam or not spam, click or don't click, patient has disease or doesn't have disease, two categories.
Okay, binary classification. How does it go from that linear calculation to a yes-no answer?
Here's the clever trick. Linear regression, as we said, outputs a raw number that could be anything, positive or negative, large or small. But for classification, we typically want something like a probability, a number between 0 and 1 representing the likelihood of belonging to the positive class, like spam being class 1.
Right, a probability makes sense for classification.
So logistic regression takes that linear combination of features, the raw number calculated, just like in linear regression, and then it feeds that number into a special mathematical function. This function is called the sigmoid function, or sometimes the logistic function, hence the name.
Sigmoid function, what does that do?
It has a characteristic S shape, and its magic property is that it takes any input number, no matter how large or small, positive or negative, and it mathematically squashes it into an output value that is always between 0 and 1.
So it converts the raw score into a probability-like value.
Exactly. So if the sigmoid function outputs 0.8, we can interpret that as the model predicting an 80% probability that the input example belongs to the positive class, class 1, for example, spam. If it outputs 0.1, it's a 10% probability.
And how does it make the final decision? Spam or not spam?
You typically set a threshold, usually 0.5. If the output probability from the sigmoid function is greater than 0.5, the model predicts the positive class, spam. If it's less than or equal to 0.5, it predicts the negative class, not spam.
So it's still about finding that optimal line or boundary in the feature space, just like linear regression.
Yes, the underlying process of finding the best weights for the features is very similar, often using gradient descent.
But then it adds that final sigmoid squashing step to turn the result into a probability between 0 and 1, which it then uses for classification.
You got it. That's the essence of logistic regression. Linear calculation inside, probability output, classification purpose. The name makes sense once you see the two parts. All right, let's shift gears to another very intuitive algorithm, decision tree learning.
Decision tree. Sounds like a flowchart.
That's a perfect way to think about it. Imagine a simple flowchart you might draw to make a decision in everyday life. Like, is the email from someone I know? If yes, does the subject line look weird? If no, does the email body contain words like Viagra or lottery?
Yeah, a series of yes-no questions leading to an action.
Exactly. Decision tree algorithms work very much like that. They automatically build a tree-like structure from your data.
How does it build this tree?
Each branching point in the tree, called a node, asks a question about a specific feature of your data. The question is usually a simple threshold test like, is feature number 3, maybe email length, less than 183 characters?
Okay, a simple test on one feature.
Right. Based on the answer, yes or no, you follow a specific branch down the tree. You continue following branches, answering questions at each node until you reach a leaf node at the bottom.
And the leaf node gives the answer.
Yep. The leaf node contains the final decision or the classification for that input example. It might say spam or not spam, for instance.
So how does the algorithm learn which questions to ask and in what order to build the best tree?
Ah, that's the learning part. The algorithm systematically searches through all the available features in your data and all the possible thresholds or split points for those features.
It tries out lots of different questions.
Yes. At each step of building the tree, it looks for the single question, the feature and threshold combination, that does the best job of splitting the current group of data points into two new groups that are as pure as possible.
Pure, meaning?
Meaning that the examples within each new subgroup are mostly, ideally entirely, of the same class or label. For example, it wants to find a question that separates the data into one group that's almost all spam and another group that's almost all not spam.
It wants to make the resulting groups less mixed up.
Exactly. It tries to reduce the impurity or uncertainty in the groups with each split. This process is often guided mathematically by concepts like Gini impurity or entropy, which are ways to measure how mixed up a group of labels is. The algorithm picks the split that results in the biggest reduction in impurity. It repeats this process recursively, building the tree branch by branch.
So it's like the machine is automatically discovering the most informative series of if and rules directly from the data itself.
That's a great way to put it. It's deriving that decision flowchart automatically.
That feels really transparent and easy to understand compared to some other methods. You could almost print out the tree and follow the logic yourself.
Absolutely. That's one of the big advantages of decision trees, their interpretability. You can literally see the decision path the model took.
Okay, decision trees make a lot of sense. Now let's circle back to the support vector machine, the SVM, that we introduced with the spam example. We talked about it finding that perfect separating wall with the biggest margin, but the book brings it up again, talking about practical challenges. Real-world data isn't always neat and tidy, right? What happens if your data points aren't perfectly separable by a simple straight line or a flat wall?
Right. That's a crucial point. The initial concept of the SVM assumes perfect separation is possible, which is rarely true in messy real-world data sets.
So how does it cope?
Well, first, let's talk about dealing with noise or slight overlaps. Sometimes you might have a few noisy data points, maybe outliers, or even just a few examples that are genuinely sitting in the wrong place, making a perfect linear separation impossible.
Yeah, like a spam email that looks almost exactly like a normal one.
Exactly. If the SVM algorithm insisted on finding a perfectly separating hard line, which is called a hard margin SVM, it might either fail completely or, worse, it might find a line that's incredibly sensitive to those few noisy points. That line wouldn't generalize well to new data.
It would be skewed by the outliers.
Right. So practical SVMs use what's called a soft margin. They introduce a bit of flexibility, Instead of demanding perfect separation, the algorithm allows some data points to be on the wrong side of the margin, or even on the wrong side of the decision boundary altogether.
It allows for a few mistakes during training.
Yes, exactly.
Yeah.
There's a tradeoff parameter, often called C, that controls this. You essentially tell the algorithm how much penalty to apply for misclassifying training examples versus how much it should prioritize maximizing the margin. It becomes a balance. Find a boundary that separates most points well and has a large margin, even if it means tolerating a few errors on the training set. This often leads to a model that works much better on new, unseen data.
Okay, so it trades off perfect training accuracy for better generalization. Makes sense. But what if the data isn't just noisy? What if the underlying pattern itself isn't linear? What if, say, the spam points form a circle around the not spam points in our feature space? You can't draw a straight line to separate that.
Ah, now you're hitting on the truly ingenious part of SVMs, dealing with nonlinearity using something called the kernel trick.
The kernel trick. Sounds mysterious.
It's really clever, almost feels like mathematical magic. The core idea is this. If your data isn't linearly separable in its original space, like your circle example in 2D,
Yeah.
maybe it would become linearly separable if you could somehow project it into a higher dimensional space.
Higher dimensions. Like transforming 2D points into 3D or 4D.
Exactly. Imagine you could add a third dimension, maybe calculated from the original two, like
Right.
distance from the center. It's possible that in this new 3D space, you could draw a simple flat plane to separate the two groups perfectly.
Okay, I can visualize that possibility. But doesn't transforming all your data into higher dimensions sound really complicated and computationally expensive, especially if you have thousands of features already?
It absolutely would be. And that's where the trick comes in. Kernel functions, or kernels, are mathematical functions that allow the SVM algorithm to get the benefit of working in that higher dimensional space without ever actually transforming the data points.
Wait, how? It operates in high dimensions without going there.
Precisely. Kernels are like shortcuts. The SVM algorithm's calculations mainly rely on computing dot products between pairs of data points, which measures their similarity. Kernel functions cleverly compute what the dot product would have been if the points had been transformed into that higher dimension, but they do it using only the original lower dimensional coordinates.
So it's a mathematical shortcut to calculate similarity in a hypothetical higher space.
Exactly. The book gives a simple example. Maybe transforming two 2D points into 3D and then taking their dot product involves a bunch of calculations. But a specific kernel function might achieve the exact same result by just doing a simpler calculation on the original 2D points and maybe squaring the result. It avoids the expensive explicit transformation, but gets the same powerful outcome.
Wow.
This allows the SVM to effectively find a linear separating hyperplane in that implicit high-dimensional space. When that hyperplane is projected back down into the original space, it corresponds to a complex, nonlinear decision boundary, like the circle you needed for your example.
Okay, that is really clever. The kernel trick is like a secret mathematical passageway, letting simple lines do complex separation work by just thinking in higher dimensions without the computational cost. That's a genuine aha.
It's one of the most powerful ideas in classical machine learning, definitely. It makes SVMs incredibly versatile.
All right.
Let's look at another fundamental algorithm, which is quite different in philosophy from SVMs or regressions. It's called k-nearest neighbors, or KNN.
K-nearest neighbors. Like finding the closest K friends.
That's a surprisingly accurate analogy. Unlike algorithms like SVM or linear regression that actively build a model, like finding that separating wall or line, and then can essentially forget the training data, KNN is different. It's often called an instance-based or even a lazy learning algorithm.
Lazy? Why lazy?
Because it doesn't really do much learning up front. It doesn't build an explicit model in the same way. Instead, it basically just keeps all of the original training data stored in memory.
It memorizes the entire training set.
Essentially, yes. The work or the computation happens only when it needs to make a prediction for a new, unseen data point.
Okay, so how does it make a prediction then, if it hasn't built a model beforehand?
It's very simple and intuitive. When a new, unseen example comes in, the KNN algorithm just looks through all the training data it has stored and finds the K training examples that are closest to this new example in the feature space.
It finds its nearest neighbors. And K is just the number of neighbors it looks for.
Exactly. K is a number you choose beforehand, like 1 or 3 or 5 or 20. So it finds the K closest points from the training set.
Okay.
For classification, if you're trying to predict a category like spam not spam or cat dog, It looks at the labels of those k nearest neighbors. The algorithm simply predicts the label that is most common among those neighbors. The majority vote wins. So if k5 and 3 neighbors are cat and 2 are dog, it predicts cat for regression. If you're trying to predict a number, like a house price, it finds the k nearest neighbors and then typically predicts the average of the numerical labels, the prices of those neighbors.
So it's literally asking the neighbors for their opinion or value and going with the consensus or average.
Pretty much.
How does it measure closeness? Just distance?
Yes, closeness is determined by a chosen distance function or metric. The most common one is the standard Euclidean distance, just the straight line distance between 2 points in that multi-dimensional feature space, like using the Pythagorean theorem. But other distance metrics can be used depending on the data.
And you said k, the number of neighbors, is something we choose.
Correct. The value of k and the choice of distance metric are hyperparameters. These are settings that you, the person using the algorithm, have to decide on before running it. The algorithm doesn't learn these itself, you provide them as configuration. Finding the best k often involves trying different values and seeing which works best on a validation set.
So it's like asking your 5 closest friends for advice versus asking your 10 closest friends. What really stands out to you about this approach? It seems almost too simple.
What's fascinating is its simplicity, absolutely. It's very easy to understand. But don't let the simplicity fool you. KNN can be surprisingly powerful, especially when the decision boundary is very complex or irregular, or when the data doesn't follow a nice, clean, global pattern that a single model like linear regression could capture. Its decisions are purely based on the local neighborhood, which gives it a lot of flexibility.
Are there downsides?
The main ones are that it requires storing the entire training dataset, which can be huge for memory. And making a prediction can be slow for very large data sets because it needs to calculate the distance from the new point to every single point in the training set to find the nearest neighbors. That's why it's called lazy, no work up front, but potentially a lot of work at prediction time.
Okay, we've covered a bunch of these core algorithms. SVMs finding boundaries, regressions finding lines, decision trees building flowcharts, KNN asking neighbors. And we keep talking about them finding optimal values or the best fit. But how do they actually do that search? You talked about finding the best line or the best wall and like 20,000 dimensions. I imagine the machine just trying every single possible line or wall until it finds the perfect one. But that sounds possibly slow, right?
Yeah.
There must be a smarter way it zeroes in on those settings.
You're absolutely right. Brute forcing every single possibility, especially in high dimensions, would take longer than the age of the universe. There's a much more efficient and really fundamental process that underlies how most of these models are trained. It's an optimization algorithm called gradient descent.
Gradient descent.
Okay.
Sounds mathematical, but you said it's fundamental.
It's incredibly important. It's not really a machine learning algorithm itself, but rather a general purpose mathematical technique for finding the minimum value of a function. Think of it like this. Imagine you're blindfolded, standing somewhere on the side of a big, bumpy mountain range, maybe in a thick fog. Your goal is to find the absolute lowest point in the valley below. You can't see the whole landscape, you don't have a map.
Okay, blindfolded on a mountain, trying to get to the bottom. How do I do it?
Well, at any point where you're standing, you can feel the ground right under your feet, right? You can feel the slope.
Yeah, which way's downhill?
Exactly. You can feel the steepness and the direction of the steepest descent. In mathematical terms, that slope information is called the gradient. It tells you which way is downhill from your current position.
So I just take a step downhill.
Precisely. If the slope is really steep downwards in one direction, you know that's the way to go, and maybe you take a fairly big step. If the ground is flatter, maybe you're getting closer to the bottom, so you take a smaller, more cautious step.
Makes sense. Take bigger steps when it's steep, smaller steps when it's flat.
Right. Now, the size of the step you take is controlled by something called the learning rate. In the book's Python code examples, it's often represented by the Greek letter alpha. The learning rate is a crucial hyperparameter you set.
Why is it crucial?
Because if your learning rate is too big, if your steps are too large, you might completely overshoot the lowest point in the valley. You could even end up bouncing back and forth from one side of the valley to the other, never actually settling in the bottom.
Okay, too big is bad. What if it's too small?
If your learning rate is too small, if your steps are tiny, you'll eventually get to the bottom. But it might take an incredibly long time, requiring millions of tiny little steps.
So finding the right step size, the right learning rate is key.
It's critical for efficient training.
Yeah.
So the whole process is iterative. 1, calculate the gradient, the slope at your current position. 2, take a small step downhill in the direction opposite to the gradient. 3, repeat.
How long do you repeat?
You keep repeating this process, calculate slope, take a step, calculate slope, take a step over and over again. Each full pass where the algorithm looks at all the training examples to calculate the overall slope is typically called an epoch. You keep running these epochs until the loss stops decreasing significantly.
What's the loss again?
The loss is just a measure of how wrong your model's predictions currently are. For linear regression, it was that sum of squared errors we talked about. The goal of gradient descent is to find the model settings, the position on the mountain, that make this loss function as small as possible. When the loss value stops going down or goes down very, very slowly, you've likely found a minimum point, the bottom of the valley, or at least a dip.
Okay.
The book uses linear regression to illustrate this really well. You can almost visualize that line of best fit starting somewhere random and then gradually, epoch by epoch, shifting its slope and intercept, moving closer and closer to the actual data points as gradient descent minimizes the squared error loss. The line descends towards the best fit.
So it's iteratively adjusting the model's internal knobs based on the direction of steepest error reduction.
That's a perfect description. For more complex models like neural networks, the mountain range is vastly more complex, with millions or billions of knobs, parameters, to adjust. But the core principle of gradient descent following the slope downhill remains the same. It's the engine that drives the learning process for many, many algorithms.
So why does this matter to you, the listener?
Well, it's basically how the machine performs that smart trial and error we talked about. It's not random guessing. It's guided by the mathematics of the gradient, constantly seeking to improve its accuracy by taking steps in the direction that reduces errors the most. It's how the machine efficiently finds those optimal values for its internal settings, allowing it to learn from data.
Now, it's really important to understand something here. While grasping the concept of gradient descent, how these algorithms iteratively find the best solutions is absolutely vital for understanding how machine learning works.
Yeah. Most machine learning engineers or data scientists working in industry today, unless they're a research scientist developing brand new algorithms from the ground up, they don't actually write the code for gradient descent or the core algorithm implementations themselves from scratch very often.
They don't. So how do they build models?
They leverage powerful open source libraries. Think of libraries as toolkits, collections of pre-written, highly optimized, and rigorously tested code for all sorts of common machine learning tasks and algorithms.
Toolkits of pre-built components.
Exactly. These libraries have been meticulously developed by experts, often by large communities or research labs. They're typically written in efficient languages like Python, often with core parts, and even faster languages like C or Fortran underneath, but they provide very easy-to-use interfaces for developers. They handle all the complex math, the optimization like gradient descent, the numerical stability issues, all behind the scenes.
Okay, so they provide the building block.
Right. The book specifically highlights a very popular Python library called scikit-learn. It's kind of the workhorse for a lot of traditional machine learning tasks.
Scikit-learn, okay.
And the book shows just how simple it makes things. For example, to train that linear regression model we discussed, using scikit-learn, it's literally just a few lines of Python code. 1, load your data, features and labels. 2, import the linear regression object from the library. 3, create an instance of that object. 4, call a single method, usually .fit, and pass your training data to it.
That's it, just .fit.
That's basically it. The library takes care of running gradient descent, or sometimes more direct mathematical solutions for simpler models like linear regression, to find the optimal parameters. And then making predictions on new data is usually just another single method call, like .predict.
Wow, that abstracts away a lot of complexity.
It really does. And what's incredibly powerful is how easy it is to swap out algorithms. If you decide linear regression isn't working well, you can often just change one line of code to import and use logistic regression instead, or SVC for a support vector machine, or decision tree classifier. The basic workflow of fit and .predict often stays exactly the same.
So the library provides a consistent interface across different algorithms.
Yes, which makes experimentation much faster.
This is a huge takeaway for you then. It means that using these powerful machine learning techniques is not restricted to only PhDs in mathematics or computer science who can implement gradient descent from scratch.
Definitely not.
These libraries democratize machine learning. They make these tools accessible to a much, much wider range of people. Software engineers, data analysts, scientists in other fields, even curious hobbyists. You can focus more on understanding your problem, preparing your data, and choosing the right tool from the toolkit rather than having to build the entire toolkit yourself from scratch every single time.
It allows people to stand on the shoulders of giants, essentially, leveraging years of development and optimization with just a few lines of code.
Okay, so we've got the algorithms. We know how they learn using things like gradient descent. And we know engineers use libraries like scikit-learn to make it practical. But the book really emphasizes something else. Getting good raw data is just the beginning. It says you can't just dump, say, raw server logs or messy sensor readings directly into an algorithm and expect magic to happen. You need to, quote, build a data set first. This sounds like it leads into something called feature engineering. What exactly is that, and why is it considered so critical for real-world projects?
You're right, the book stresses this, and it's absolutely crucial. Feature engineering is often described, maybe slightly dramatically, as where the black art of machine learning lies. It's frequently the most labor-intensive part of a project, and also the place where creativity and domain expertise can make the biggest difference.
More important than the algorithm sometimes.
Often, yes. A decent algorithm with great features will almost always outperform a state-of-the-art algorithm with poor features. Feature engineering is the whole process of transforming that raw, messy, real-world data into the clean, numerical feature vectors that the machine learning algorithms actually expect and can learn from effectively.
So it's the bridge between raw data and the algorithm's input.
Exactly. And it requires a lot of thought, creativity, and often deep domain knowledge. That means really understanding the subject matter you're working with, understanding medicine if you're building a diagnostic tool, or finance if you're building a fraud detector.
Can you give some examples from the book?
Sure. The book uses an example of having raw logs of how customers interact with, say, a software product. You can't feed those raw log lines into most algorithms. A data analyst would need to engineer features from those logs.
Like what kind of features?
Things like calculating the price of the subscription the user has, figuring out the frequency of connections per day or per week, calculating the average session duration in seconds, maybe the number of times they used a specific feature, or the average server response time they experienced.
So deriving meaningful numbers from the raw activity.
Exactly. These aren't directly present in the raw logs. They are calculated, aggregated, summarized insights. The goal is to create features that are informative, features that have high predictive power. You're trying to capture the aspects of the raw data that are most likely to help the algorithm make accurate predictions about whatever you're trying to predict. Like, will this customer stop using the product?
Okay, so deriving new features is a big part. What else falls under feature engineering?
There are several common techniques used to prepare existing data too. One-hot encoding. We touched on this. If you have a feature that's categorical, like color with values red, yellow, green, many algorithms need numbers. You can't just map them to 1, 2, 3 because that implies an order. Green is somehow more than red. One-hot encoding turns this single color feature into 3 new binary or 1 features. Is eyes yellow is green. An example that was red would get 100 for these 3 features.
Right, avoids fake ordering.
Yep. Binning or bucketing. This is kind of the opposite. If you have a continuous numerical feature like age, you might group it into discrete categories or bins. For example, 0, 5 years, 6, 10 years, 11, 15 years, etc.
Why would you do that? Lose information.
Sometimes it helps. It can give the algorithm a hint that maybe the exact age doesn't matter as much as which general age group someone falls into. It can sometimes make the patterns easier for simpler models to learn. Normalization and standardization. These are techniques for rescaling numerical features so they all fall within a similar range. For example, mapping all values to be between 0 and 1, or making them have an average of 0 and a standard deviation of 1.
Why is scaling important?
2 main reasons. First, many algorithms, especially those using gradient descent or relying on distance calculations like KNN or SVMs, can learn much faster and perform better if all features are on a similar scale. It prevents features with naturally large values, like house prices, from dominating the learning process compared to features with small values, like number of bedrooms. Second, it can help avoid numerical instability issues in the computer when dealing with very large or very small numbers. Generally, scaling features is a good default step. Dealing with missing features. Real-world data is almost always messy and have gaps. What do you do if an email sender is unknown or a patient's specific lab test wasn't done?
Yeah, what do you do?
Several strategies. You could just remove the examples rows that have missing values, but only if you have lots of data to spare. Some algorithms are specifically designed to handle missing values gracefully. Or you can use data imputation techniques.
Imputation, filling in the gaps.
Exactly. It could be simple, like replacing a missing age with the average age of everyone in the data set. Or it could be more sophisticated, like using another machine learning model just to predict what the missing value likely was based on the other features for that example.
Wow, using ML to fix data for ML meta.
It gets quite sophisticated.
So what does all this feature engineering stuff mean for you, the listener? It really highlights that the secret sauce in a successful machine learning project isn't always just about picking the most advanced algorithm. Often the real breakthrough comes from how cleverly the raw information is cleaned, transformed, and presented to the machine through thoughtful feature engineering. It's about translating the messy complexity of the real world into a language the algorithm can actually understand and learn meaningful patterns from.
Couldn't have said it better myself. It's where domain expertise meets data skills. Okay, so you've painstakingly engineered your features, your data is clean and numerical. Now you face another big decision. With all these algorithms we've discussed, linear regression, logistic regression, SVM, decision trees, KNN, and many others, how do you actually pick the right one for your specific problem and data set?
Yeah, it seems like a lot of choices. Is there a flowchart for picking the algorithm?
Not quite a perfect flowchart, but the book suggests a very practical approach, asking yourself a series of diagnostic questions to help narrow down the possibilities and guide your selection.
Okay, what kind of questions?
First off, a really important one, explainability. Do you need to be able to explain why the model made a specific prediction? Maybe to a non-technical colleague, a manager, a customer, or even a regulator.
Right, like explaining why someone was denied a loan.
Yeah, exactly. Some algorithms, especially complex ones like deep neural networks, are often referred to as black boxes. They might be incredibly accurate, but it's very difficult, sometimes impossible, for a human to understand precisely why they produced a certain output based on a given input.
They just work, but you don't know how.
Pretty much. On the other hand, simpler models like linear regression, logistic regression, or decision trees are much more transparent or interpretable. You can often look at the model's coefficients or trace the path through the decision tree to understand the reasoning. So if explainability is a critical requirement for your application, you might lean towards these more interpretable models, even if they are slightly less accurate than a black box alternative.
Okay, explainability. What else?
Next, think about your data size relative to your computer's memory. In memory versus out of memory. Can your entire data set fit comfortably into your computer's RAM?
Did that matter?
It does for algorithm choice. Many standard algorithms, especially in libraries like scikit-learn, assume the whole dataset can be loaded into memory at once for training. If your dataset is massive terabytes, maybe, and won't fit in RAM, you'll need to look for algorithms or implementations that support out-of-core or incremental learning, meaning they can learn by processing the data in smaller chunks or batches without needing everything loaded simultaneously.
Okay, memory constraints. Makes sense.
Then, consider the sheer number of features and examples. How many rows examples and how many columns features does your dataset have?
Millions. Billions.
Some algorithms scale better with a huge number of examples. Others handle a vast number of features more gracefully. For instance, linear models and some tree-based methods can often handle very high-dimensional data, lots of features, quite well.
So the shape of the data matters.
Definitely. Also, the type of features. Are they predominantly categorical, numerical, or a mix? As we saw with feature engineering, some algorithms inherently handle categorical features, like some tree methods, while others strictly require numerical input, meaning you'd need to do things like one-hot encoding first if you choose them.
Gotcha. What about the patterns in the data?
That's a key one. Non-linearity of the data. Can the relationship between your input features and the output you're trying to predict be reasonably approximated by a straight line or a flat plane, linear? Or is the underlying relationship likely more complex, curvy, or involves interactions between features, nonlinear?
How do you know?
Sometimes visualization helps, or domain knowledge. But if you suspect the relationship is nonlinear, simpler models like basic linear regression might underfit. You might need to consider more complex models like SVMs with nonlinear kernels, decision tree ensembles, or neural networks that are specifically designed to capture complex nonlinear patterns.
Okay, linearity. Anything else?
Finally, practical constraints like training speed and prediction speed. How quickly does the model need to be trained? Some models, especially deep neural networks, can take days or even weeks to train on large data sets. Simpler models train much faster. And once trained, how fast does it need to make predictions? If you're building a system for real-time bidding in online advertising, predictions need to happen in milliseconds. Some models are very fast at prediction, like linear models, while others might be slower, like KNN on large data sets.
So speed matters too.
Absolutely. So by asking these questions, explainability, memory, data size, feature types, linearity, speed, you can start to narrow down the field from dozens of potential algorithms to a more manageable shortlist of promising candidates for your specific task.
And the ideal approach, if you have time.
If time and resources permit, the best practice is often to try out several algorithms from your shortlist. Train each one on your training data, tune their hyperparameters using your validation data, and then see which one performs best according to your chosen evaluation metric. But these questions provide a really valuable framework for making an informed initial selection.
Right, so you've gone through all that hard work, you got the data, you meticulously engineered the features, you thoughtfully selected a few candidate algorithms, maybe using those questions you just outlined, and you've trained a model using a library like scikit-learn. Now, the moment of truth, how do you actually know if the model you built is any good? And we already established it's not enough for it to do well on the data it was trained on, right? That feels like a student grading their own homework they already have the answers to.
Exactly. Evaluating a model only on the data it was trained on tells you almost nothing about how it will perform in the real world on new, unseen data. That grading your own homework analogy is perfect. It leads to overfitting, where the model has just memorized the training answers, noise, and all.
So how do we evaluate it properly, fairly?
The absolute standard practice, the bedrock of reliable model evaluation, is to split your initial data set meticulously before you even start training. You typically divide it into 3 distinct sets.
3 sets. Okay, what are they?
1, the training set. This is usually the largest chunk of your data, maybe 60–80%. This is the only data the algorithm gets to see during the actual learning process, the data used to adjust its internal parameters, like the weights in linear regression or the structure of a decision tree.
Okay. Training set is for learning.
2, the validation set. This is a smaller portion, maybe 10–20%. This data is held out during training. Its crucial role is for tuning hyperparameters, like the K in KNN, or the C penalty term in SVM, or the learning rate in gradient descent, and for making decisions about which algorithm or which feature set works best. You train different versions of your model on the training set, and then you see how well each version performs on this validation set. The model never learns directly from the validation data's labels, but you use its performance on this set to guide your choices.
So validation set is for tuning and choosing the best model configuration. It's like practice quizzes before the final exam.
That's a great analogy. It helps you pick the best study strategy without using up the actual final exam questions.
Okay, and the third set.
3, the test set. This is also typically 10–20% of the data, and it's the most precious. It's kept completely separate, locked away until the very end. After you've done all your training, all your hyperparameter tuning using the training and validation sets, and you've selected your single final best model, only then do you unleash it on the test set.
And this gives the final score.
Yes. The performance on the test set provides the most realistic, unbiased estimate of how your chosen model is likely to perform on brand new, unseen data in the real world. Because the model has never seen this data in any way during its development or tuning process, it's the fairest possible assessment.
So why the need for 3 sets? Why not just training and test?
It's a subtle but critical point about avoiding information leak. If you only had training and test sets, you might try lots of different hyperparameters or algorithms, evaluate them all on the test set, and pick the best one. But in doing so, you implicitly use the test set results to guide your model selection. You've indirectly overfitted to the test set through your choices. The validation set acts as that intermediate buffer, allowing you to make all those tuning decisions without touching or biasing your final, truly independent test set evaluation. It preserves the integrity of the final performance measure.
Ah, okay. The validation set lets you fiddle and tune without contaminating the final grade from the test set. That makes sense.
Now, this whole process directly relates back to those core problems of underfitting versus overfitting, which are often framed in terms of the bias-variance trade-off.
Bias and variance. Can you break those down simply?
Sure. Think of bias as the errors coming from your model being too simple. It makes overly simplistic assumptions about the data. An underfit model has high bias. It can't even capture the underlying patterns in the training data well. It's consistently wrong, like trying to fit that complex curve with a straight line.
Too simple. Makes lots of errors even on training data. That's high bias.
Right. Now think of variance as the errors coming from your model being too complex, too sensitive to the specific training data it saw. An overfit model has high variance. It fits the training data perfectly, including the noise, but it changes wildly if you train it on a slightly different training set. It doesn't generalize well to new data because it learned the noise, not the signal.
Too complex. Fits training data perfectly, but fails on new data. High variance.
Exactly. And the trade-off is that these two often work in opposition. If you make your model more complex to reduce bias, fit the training data better, you often increase its variance, risk overfitting. If you make your model simpler to reduce variance, make it more stable and less prone to overfitting, you often increase its bias, risk underfitting.
So you can't minimize both completely. You have to find a balance.
Finding that sweet spot, the model complexity that balances bias and variance to give the best performance on unseen data, like the validation or test set, is the core challenge of model building.
How do you fight overfitting, that high variance problem?
Besides getting more training data, which always helps, one of the most powerful techniques is regularization.
Regularization, like making the model more regular or simple.
That's exactly the intuition. Regularization methods are techniques that essentially add a penalty to the learning process. They discourage the algorithm from building an overly complex model.
How does adding a penalty help?
During training, the algorithm tries to minimize the loss, the error. Regularization adds an extra term to this loss function, a penalty term. This penalty term gets bigger if the model's parameters, its internal settings, become too large, or if the model relies too heavily on too many features.
So it punishes complexity.
Yes. It forces the algorithm to find a balance between fitting the training data well, lowering the original loss, and keeping the model simple, keeping the penalty term low. This often means accepting slightly higher bias, maybe not fitting the training data quite as perfectly, in order to achieve a significant reduction in variance, making it generalize much better to new data.
It's intentionally making the model a bit dumber on the training data so it's smarter on new data.
That's a good way to think about it. The book mentions the two most common types. L1 regularization, lasso, tends to push some model parameters to become exactly zero, effectively performing automatic feature selection by ignoring some inputs. This can make models simpler and more interpretable. L2 regularization, RIG, encourages parameters to be small, but rarely exactly zero. It generally gives slightly better predictive performance on unseen data and is often the default choice.
Okay, so regularization is a key tool for controlling complexity and improving generalization. So we've trained our model, we've evaluated it using our test set to avoid overfitting. But how do we actually measure that performance? Is it just about counting how many predictions the model got right? You mentioned earlier, especially for things like spam detection, that simple accuracy might not tell the whole story. Some mistakes are worse than others.
You're absolutely right. Simple accuracy, just calculating correct predictions, total predictions, can be misleading, especially in two common scenarios. One, when the cost of different types of errors is very different, like your spam example. A false positive, flagging a real email as spam, is usually much worse than a false negative, letting a spam email through. One, when the cost of different types of errors is very different, like your spam example. Two, when you have imbalanced classes, imagine building a model to detect a rare disease that only affects burn at 1% of the population. A model that just predicts everyone is healthy would be 99.9% accurate, but it would be completely useless because it never finds the people who actually have the disease.
Right, 99.9% accuracy sounds great, but it's meaningless there. So what metrics give us a better picture?
To get a more nuanced understanding, especially for binary classification, two classes, we often start by looking at the confusion matrix.
Confusion matrix. Sounds confusing.
It's just a simple table, really. It breaks down all the predictions your model made on the test set into 4 distinct categories based on the actual true label versus the predicted label.
Okay, 4 categories. What are they?
Let's stick with the spam example. Spam positive, not spam negative. True positive, TP. The email was actually spam positive, and the model correctly predicted it as spam positive. Good. False negative, FN. The email was actually spam positive, but the model incorrectly predicted it was not spam negative. This is a missed spam. The model failed to detect it. False positive, FP. The email was actually not spam negative, but the model incorrectly predicted it was spam positive. This is a false alarm. A legitimate email wrongly flagged. True negative, TMN. The email was actually not spam negative, and the model correctly predicted it was not spam, negative. Also good.
Okay, TPFN, FPTN. Got it.
Yeah.
It tallies up all the rights and wrongs in detail. How does this help?
Because from these 4 numbers, we can calculate much more informative metrics, like precision and recall.
Precision and recall. What do they measure?
Precision answers the question, of all the emails that my model predicted were spam, how many actually were spam?
So how trustworthy are the spam predictions?
Exactly. It's calculated as TP plus FP. High precision means the model makes very few false positives. When it says something is spam, it's very likely correct. You minimize those annoying false alarms.
Okay, high precision, fewer false alarms. What about recall?
Recall, also sometimes called sensitivity, answers the question. Of all the emails that truly were spam in reality, how many did my model correctly identify?
So how much of the actual spam did it catch?
Right. It's calculated as TP plus FN.
What?
High recall means the model makes very few false negatives. It finds most of the spam that's out there.
High recall, fewer misses. Can you have both high precision and high recall?
Often there's a trade-off between them. If you adjust your model to be really cautious about calling something spam, to maximize precision and avoid false alarms, you'll probably end up missing more actual spam emails, lowering recall. Conversely, if you make the model very aggressive in catching spam to maximize recall, you'll likely end up flagging more legitimate emails incorrectly, lowering precision.
So you have to choose which is more important for your specific problem.
Exactly. For spam detection, as we discussed, you typically prioritize high precision. You really don't want important emails going to the spam folder, low false positives. You might be willing to tolerate slightly lower recall, meaning a few spam emails might still sneak into your inbox, some false negatives. But for detecting that rare disease we talked about, you'd want extremely high recall, even if it means lower precision. More false positives, i.e. healthy people getting unnecessary follow-up tests. Missing a real case, a false negative, would be catastrophic.
The context dictates the priority. Makes total sense. Are there other metrics?
Yes, another very common and useful one, especially for classifiers that output a probability or a confidence score, like logistic regression, is the area under the ROC curve, AUC.
ROC curve, AUC.
The ROC curve plots the true positive rate, recall, against the false positive rate across all possible decision thresholds. The AUC is the area under that curve. It gives you a single number between 0 and 1 that summarizes the model's overall ability to distinguish between the positive and negative classes, irrespective of the specific threshold chosen. A perfect classifier has an AUC of 1.0. A model that just guesses randomly has an AUC of 0.5. Higher AUC generally means a better classifier overall.
Okay, so AUC gives a good summary score of the model's discriminatory power.
It's a very popular metric for comparing different classifiers.
So the big takeaway here for you is that just looking at overall accuracy isn't enough. Defining what good performance means is subjective and depends entirely on the specific problem and the real-world consequences of different kinds of errors. You need to choose the right metric precision, recall, AUC, or others that truly reflects the goals of your application.
Okay, one last crucial step in the practical process of building a good model. Remember when we talked about algorithms like KNN or SVM and mentioned there were settings like K, the number of neighbors, or C, the penalty term, that we, the users, have to choose before training starts?
Yeah, the ones the algorithm doesn't learn itself from the data, the configuration settings.
Exactly. Those are called hyperparameters. They control the learning process itself or define the model structure. Finding the best values for these hyperparameters is called hyperparameter tuning or hyperparameter optimization. It's like dialing in the knobs on a machine to get it running perfectly.
How do you find the best settings? Just guess.
Definitely not just guessing. It's usually a process of systematic experimentation. A very common and straightforward approach, especially if you don't have too many hyperparameters to tune, is called grid search.
Grid search, like searching on a grid.
Precisely. You first define a grid of specific values you want to try for each hyperparameter. For example, for the K in KNN, you might try values like 1, 3, 5, 7, 9, 11. For the C in SVM, you might try 1, 1, 10, 100.
So you list out the options you want to test.
Right. Then the grid search process automatically trains and evaluates a separate model for every single possible combination of these hyperparameter values. So if you try 6 values for K and 4 values for C, you'd end up training and evaluating 6-4 always 24 different models.
Wow, okay. Where does it evaluate them? On the training set?
No.
Yeah.
Crucially, it evaluates each of these 24 models on the validation set, that separate chunk of data we held out specifically for this purpose.
using the validation set to compare the different settings.
Exactly. You calculate your chosen performance metric, like accuracy, AUC, precision, etc., on the validation set for each of the 24 models. Then you simply pick the combination of hyperparameters, the specific K and C values in our example, that resulted in the best performance on the validation set.
So it systematically explores the grid and pick the winner based on validation performance.
That's grid search in a nutshell. It's simple and exhaustive for the grid you define.
What if you don't have enough data to make a separate validation set? You mentioned that can happen.
Good question. That's where cross-validation CV comes in. Cross-validation is a clever technique to get a reliable estimate of model performance and tune hyperparameters even when you have limited data.
How does cross-validation work?
The most common type is K-fold cross-validation. Confusingly, this K is different from the K in KNN. Let's say you choose 5-fold CV. You take your training data, not the test set, and randomly split it into 5 equal-sized chunks or folds.
Okay, split the training data into 5 parts.
Then you repeat the training process 5 times. In the first run, you use folds 1, 2, 3, and 4 for training and use fold 5 for validation. In the second run, you use folds 1, 2, 3, and 5 for training and use fold 4 for validation, and so on, rotating which fold serves as the validation set each time.
So each fold gets a turn being the validation set.
Exactly. You train and validate 5 models in total for a specific set of hyperparameters. You then average the performance score you got across those 5 validation folds. This average score gives you a more robust and reliable estimate of how well that particular set of hyperparameters performs than just using a single validation split, especially with smaller data sets.
And you can combine this with grid search.
Absolutely. You'd run the entire 5-fold cross-validation process for each combination of hyperparameters in your grid. You then choose the hyperparameter combination that yielded the best average cross-validated performance. It's computationally more expensive, but gives you more confidence in your tuning.
Okay, so it's all about systematically experimenting, whether using a simple validation set or more robust cross-validation to find that sweet spot for your model settings. It's definitely more science and art, really methodical testing to optimize performance.
Precisely. It takes the guesswork out and replaces it with empirical evidence based on how the model performs on data it wasn't directly trained on during that specific run.
This has been incredibly insightful, covering the whole workflow from data prep to evaluation. Now, the 100-page machine learning book, like many resources today, eventually gets to the really big topic, the one that seems to dominate headlines: neural networks, and especially deep learning. What are these at their core? And why have they become such a driving force in AI recently?
Right. It's impossible to talk about modern machine learning without touching on neural networks and deep learning. At its heart, a neural network, despite the biological-sounding name, is really just a sophisticated mathematical function. But it's a special kind. It's built by nesting functions within functions, creating layers of computation.
Layers? Like an onion?
Sort of. Imagine a series of mathematical layers. The input data goes into the first layer. That layer performs some calculation, often similar to linear regression, multiplying inputs by weights and adding a bias, and then passes the result through an activation function.
Activation function.
That's usually a nonlinear function, something that introduces curves or thresholds. It's this nonlinearity that's absolutely critical. It's what allows neural networks to learn complex patterns that simple linear models can't. The output of the first layer's activation function then becomes the input to the next layer, which does its own calculation and activation and so on, layer after layer.
Okay, a chain of layers doing calculations and nonlinear transformations. What makes it deep learning?
Deep learning simply refers to neural networks that have multiple hidden layers. Hidden layers are all the layers between the initial input layer and the final output layer. Historically, networks with just one hidden layer were common, but deep usually implies 2 or more hidden layers, often many, many more.
Why are multiple layers better? Why deep?
The power of depth, of having multiple layers, lies in their ability to learn a hierarchy of features or patterns, building up complexity layer by layer.
Hierarchy. Like simple things first, then complex things.
Exactly. Think about image recognition again. The first hidden layer in a deep network might learn to detect very basic things like simple edges, corners, or color blobs directly from the raw pixels. The next layer takes those detected edges and corners as input and might learn to combine them to form slightly more complex shapes: circles, squares, simple textures. A subsequent layer might combine those shapes to recognize parts of objects: an eye, a wheel, a nose. And finally, the layers closer to the output can combine those parts to recognize whole objects: a face, a car, a cat.
So each layer learns increasingly abstract and complex representations based on the output of the layer before it.
Precisely. This hierarchical learning allows deep networks to tackle incredibly complex tasks, like understanding natural language or generating realistic images that were very difficult for shallower methods.
Were there challenges in making them deep?
Oh, absolutely. For a long time, training very deep networks was extremely difficult due to a problem called the vanishing gradient problem.
Vanishing gradient. The slope signal disappears.
Essentially, yes. Remember, gradient descent uses the slope gradient to update the model's parameters. In very deep networks, as that error signal propagated backward from the output layer to the earlier layers during training, it could get smaller and smaller and smaller at each step. By the time it reached the earliest layers, the gradient signal was so tiny, almost zero, that those layers barely learned anything at all. They were effectively untrainable.
So the learning signal died out before reaching the start.
Right. But this has been largely overcome in the last decade or so thanks to several breakthroughs. New types of activation functions, like the RILE function, clever ways to initialize the network's weights, better optimization algorithms, and specialized network architectures designed to help the gradient flow better, like residual connections or LSTMs, which we'll touch on. These advances are what unleash the power of truly deep learning.
Okay, so deep learning, multiple layers learning, hierarchical features, and we've mostly solved the training problems now. Let's quickly touch on two really important types of deep networks the book mentions, CNNs and RNNs.
Definitely. First, convolutional neural networks, CNNs. Purpose. These are the superstars for anything involving grid-like data, especially images. They are behind most modern computer vision successes, but they also work surprisingly well on other data like text or even audio spectrograms. Intuition. The key idea is locality and translation invariance. In an image, important features, like the edge of an object or the texture of fur, tend to be local patterns. And that same pattern, like a cat's ear, could appear anywhere in the image.
Right, a cat's ear is cat's ear, whether it's top left or bottom right.
Exactly. So instead of connecting every input pixel to every neuron in the first hidden layer, which would require a massive number of parameters, CNNs use small filters or kernels. Think of these as tiny, learnable pattern detectors. Each filter is specialized to recognize a specific local pattern, like a horizontal edge, a specific curve, or a color gradient.
So like little magnifying glasses looking for patterns.
Yeah, and these filters slide across the entire input image, patch by patch, looking for their specific pattern everywhere. This operation of sliding a filter and calculating its response is called convolution. Because the same filter, the same pattern detector, is used across the whole image, it drastically reduces the number of parameters the network needs to learn, making CNNs much more efficient for high-dimensional data like images. And by stacking multiple layers of these convolutions, CNNs build up that hierarchical understanding. Simple edges combine to form textures, textures combine to form parts, parts combine to form objects.
Okay, CNNs use sliding filters to find local patterns efficiently. Great for images. What about RNNs?
Second, recurrent neural networks, RNNs. Purpose. These are designed specifically for sequential data, where the order of elements is crucial. Think of processing text, sequences of words, speech, sequences of sounds, or time series data, like stock prices over days. Intuition. Unlike standard feed-forward networks, like basic neural networks or CNNs, where information flows strictly in one direction from input to output, RNNs have loops. They have an internal state or memory that gets updated as they process each element in the sequence.
Loops and memory. How does that work?
As the RNN reads, say, the first word in a sentence, it processes it and updates its internal memory state. When it reads the second word, it processes that word along with the memory state carried over from the first word. This allows the network's output at any point in the sequence to be influenced by all the preceding elements. It gives them context.
So it can remember what happened early in the sequence.
That's the idea. For example, in the sentence, the cat chased the mouse and it was fast, a good RNN should be able to figure out that it refers to the mouse, or maybe the cat, based on the context stored in its memory from processing the earlier words.
Okay, that's powerful for sequences. Are there issues?
Yes. A major challenge with basic RNNs was handling long-term dependencies. They could often forget information from much earlier in a long sequence. The memory state could get washed out by more recent inputs.
Like forgetting the beginning of a long paragraph.
Exactly. This is where more advanced variants came in, particularly LSTMs, long short-term memory, and GRUs, gated recurrent units. These are special types of RNN units that have internal gates.
Gates? Like traffic control.
Sort of. These gates are like little neural networks themselves, and they learn to control the flow of information within the memory cell. They decide what old information to forget, what new information to store, and what information to output. This gating mechanism allows LSTMs and GRUs to selectively remember relevant information over much longer periods, making them incredibly effective for tasks like machine translation, speech recognition, and text generation. So deep learning is huge, especially in supervised and sometimes reinforcement learning. But the book also revisits unsupervised learning with some more advanced techniques, particularly for finding structure in unlabeled data. Two big areas here are clustering and dimensionality reduction.
Right, unsupervised, no labels, just finding patterns. We talked about clustering before, like grouping Legos. Are there specific ways machines do that?
Yes, several popular algorithms exist. K-means, this is probably the most well-known clustering algorithm due to its simplicity. You, the user, have to tell it K, the number of clusters you expect to find beforehand.
You have to guess the number of groups.
Often, yes, or use other methods to estimate it. K-means then works iteratively. It randomly places K starting points, called centroids. Then it repeats two steps. 1. Assign each data point to the cluster whose centroid is nearest. 2. Recalculate the position of each centroid to be the average location of all points assigned to it. It keeps doing this until the cluster assignments don't change much anymore.
Okay, assign points, move centers, repeat. What kind of clusters does it find?
K-means tends to find clusters that are roughly spherical or blob shape, and it assumes clusters are relatively similar in size. DBSCAN, HDBSCAN. These are density-based clustering algorithms. They work differently. They define clusters as dense regions of data points separated by sparser regions.
Based on how crowded the points are.
Exactly. An advantage is that they can find clusters of arbitrary shapes, not just spheres, and they are good at automatically identifying outliers points that don't belong to any dense cluster. Crucially, you generally don't need to specify the number of clusters beforehand with these methods, especially HDBSCAN. The algorithm figures it out based on the data's density structure.
That sounds more flexible if you don't know the number of groups. How do you figure out K for K-means if you need to?
That's a common problem. The book suggests there are more principled ways than just guessing, like using statistical methods such as the elbow method, silhouette score, prediction strength, or the gap statistic to help estimate a reasonable number of clusters based on the data structure.
Okay, so ways to estimate K. What about the other unsupervised area, dimensionality reduction? You mentioned it simplifies data, often for visualization.
Right. Dimensionality reduction aims to reduce the number of features, the dimensions, in your data set while trying to preserve as much of the important information or structure as possible.
Why do it again?
Primarily for visualization, as you said. Humans are terrible at visualizing data beyond 2 or 3 dimensions. If your data set has 50 features, you can't easily plot it to see patterns. Dimensionality reduction techniques can project that 50D data down to 2D or 3D, allowing you to create scatter plots where you might visually identify clusters, trends, or outliers. It's also sometimes used to simplify data before feeding it into another machine learning algorithm, potentially reducing noise or computational cost.
What are some common techniques? Principal component analysis, PCA. This is a classic, widely used linear technique. PCA finds the directions, the principal components, in your high-dimensional data, along which the data varies the most. It then projects your data onto a smaller number of these principal components, effectively rotating your data and discarding the directions with the least variation. It's great for data compression and noise reduction while retaining maximum variance, UMA and TSNE. These are more modern, non-linear techniques that are particularly fantastic for visualization. Their goal is slightly different from PCA. They try to create a low-dimensional, usually 2D or 3D map of your high-dimensional data, such that points that were close together in the high-dimensional space remain close together in the low-dimensional map. They're often incredibly good at revealing the underlying cluster structure or manifold structure of complex datasets in a way that PCA might miss. They are staples for visualizing high-dimensional biological or text data, for instance. Autoencoders. These are actually a type of neural network used for unsupervised learning. An autoencoder tries to learn a compressed representation of its input. It has an encoder part that squishes the input down into a lower dimensional bottleneck layer and a decoder part that tries to reconstruct the original input from that compressed representation. The compressed representation in the bottleneck layer is effectively a dimensionality reduction. Autoencoders. Hashtag tag 5.3. Other cutting-edge learning paradigms. Wow, the field keeps expanding.
Beyond these core supervised, unsupervised, and deep learning methods, what are some other really fascinating or cutting-edge ways machines are being taught to learn that the book touches on? It feels like we're just scratching the surface.
We really are. The field moves incredibly fast. The book gives a nice introduction to several other intriguing learning paradigms that tackle specific, often challenging problems.
Like what?
Okay, one really cool area is one-shot learning.
One shot. Learning from just one example.
Exactly. The goal is to train a model that can successfully recognize a new object category, or maybe a specific person's face, after having seen only one single example of it during training.
How is that even possible?
Yeah.
Usually ML needs thousands of examples.
It's a different approach. Think about facial recognition on your phone. You probably only registered your face once or maybe a few times, right? Yet it recognizes you reliably. That's an application. It often works by training the model not to classify objects directly, but to learn a good similarity function or embedding space. It learns to map images into a vector space such that images of the same object person are mapped very close together, while images of different objects persons are mapped far apart. Then, to recognize a new object from one example, it just needs to see if the new image maps close to that single example in the embedding space. Techniques like Siamese neural networks and triplet loss are common here.
Learning similarity, not categories directly.
Yeah.
Clever. What else?
Even more ambitious is zero-shot learning.
Hero shot. Learning with no examples. Now you're kidding me.
Almost. It means training a model to predict labels or categories that it has never explicitly seen during its training phase.
How on
It relies on auxiliary information, often semantic information about the labels themselves. Imagine you train an image classifier on lots of animals, dogs, cats, bears, horses, but you never show it a single picture of a zebra.
Okay.
But maybe the model also has access to information about the word zebra, perhaps from word embeddings we discussed earlier, knowing that zebra is associated with attributes like has stripes, is a mammal, looks like a horse. If the image classifier sees a new picture and detects features corresponding to stripes, mammalness, and horse-like shape, it might be able to infer that this must be a zebra, even without ever having been explicitly taught what a zebra looks like from an image. It bridges the gap using semantic relationships.
Connecting visual features to word meanings. That's mind-bending.
It's a very active research area. Then there's active learning.
Active learning. The machine takes initiative.
In a way, yes. This is super useful when getting labeled data is very expensive, or time-consuming, think expert medical image annotation, or classifying complex legal documents. Instead of just passively receiving labeled data, an active learning system tries to intelligently select which unlabeled examples it should ask the human expert to label next.
How does it choose?
It typically prioritizes the examples it's most uncertain about, or examples that lie near the current decision boundary, or examples that are in very dense regions of the unlabeled data. The idea is that getting labels for these specific points will provide the most information and help the model improve the fastest, making the expensive labeling process much more efficient. It's like a smart student asking precisely the right questions to clarify their biggest doubts.
Maximizing the value of each label. Very practical.
Very. And then there's learning to rank.
Learning to rank.
Yeah.
Like search engine results.
Exactly. That's a prime application. Standard classification might just say if a web page is relevant or not relevant to a query. Learning to rank goes further. It optimizes the ordered list of results. It learns to predict the optimal position for each document in the rank list presented to the user, considering factors beyond simple relevance, like diversity or authority. It uses specialized metrics that evaluate the quality of the ranking itself.
Okay. Optimizing the order. What about recommendations?
Yes, elaborative filtering. This is the engine behind most recommendation systems. Users who like this item also liked, or based on your viewing history, you might like.
How does it work? Magic.
Close. It works by analyzing patterns across many users' preferences or behaviors. It typically uses a large, very sparse matrix, where rows are users, columns are items, like movies or products, and the entries are ratings or interactions, like watched or purchased. The core idea is to find users with similar tastes or items with similar appeal, and then recommend items that similar users liked but the current user hasn't seen yet. The book mentions techniques like factorization machines and denoising autoencoders, which are good at handling the sparsity. Most users haven't rated most items, and finding latent underlying factors that explain user preferences.
Finding hidden connections between users and items.
Exactly. And one last one that's super important, self-supervised learning.
Self-supervised, learning from itself.
Yes, this is a really powerful idea for leveraging vast amounts of unlabeled data. The trick is to create a pretext task where the model generates its own labels from the structure of the unlabeled data itself and then learns to solve that task.
Creating its own homework from the textbook.
That's a great analogy. A prime example the book gives is learning word embeddings, like the famous word-to-vec algorithm. How you learn that king is similar to queen and man is similar to woman just from raw text without any human labels.
Yeah.
The skipgram model, part of word2vec, does this using a pretext task. It takes a word from a sentence, say fox, and tries to predict the words that are likely to appear nearby in the context, like predicting quick, brown, jumps. It uses the surrounding words as the labels. By training a neural network to do this prediction task across billions of words in massive text corpora, the network implicitly learns rich numerical vector representations, embeddings, for each word, where words used in similar contexts end up with similar vectors. The text itself provides the supervision. This has revolutionized natural language processing.
Wow, using the data's own structure to create learning signals. That's incredibly resourceful. Okay, that's a whirlwind tour of advanced learning paradigms. One final practical point the book raises. It's one thing for an algorithm to work mathematically, to be able to learn and make accurate predictions, but in the real world, especially with the enormous data sets we often deal with now, it also needs to work fast enough to be usable. How do engineers and researchers think about the efficiency or speed of these algorithms?
That's an absolutely critical consideration in practice. A theoretically perfect algorithm that takes centuries to run on your dataset is, well, useless. Algorithmic efficiency is all about analyzing how an algorithm's resource requirements, typically its running time, or sometimes the amount of memory space it needs, grow as the size of the input data increases.
How performance scales with data size.
Exactly. The standard way computer scientists talk about this is using big O notation.
Big O, like, oh no, this is going to be slow.
Sometimes. Big O notation provides a high-level way to classify an algorithm efficiency by describing its growth rate in the worst-case scenario. For example, an algorithm with ON complexity, read order n or big O of n, means its running time grows linearly with the input size n. If you double the input data size, the running time roughly doubles. This is generally considered quite efficient. An algorithm with ON2 complexity, order n squared, means its running time grows quadratically. If you double the input size, the running time roughly quadruples, 2 squared. This can become very slow very quickly for large n. An algorithm with O log n, complexity, order log n, is even better than linear. The time increases very slowly as n grows. An algorithm with O1 complexity, order 1, or constant time, means its running time doesn't depend on the input size at all. It takes the same amount of time regardless of how much data you give it. Rare but ideal.
So Big O gives you a shorthand for how well an algorithm scales.
Precisely. The book gives a simple illustration. Imagine you have a list of numbers, and you want to find the two numbers in the list that have the largest difference between them. A naive approach might be to compare every number in the list to every other number, keeping track of the biggest difference found. If the list has n numbers, this involves roughly n comparisons, so it's an ON2 algorithm.
Comparing everything to everything else?
Yeah.
Slow for long lists.
Right. But a much smarter approach would be to simply scan through the list once to find the minimum value, and scan through it once again, or do it in the same scan, to find the maximum value. Then just subtract the minimum from the maximum. Finding the min and max each takes roughly n steps, so the whole process is ON.
Much faster. Linear instead of quadratic.
Exactly. For a list of 1,000,000 numbers, ON is vastly faster than ON2. Understanding Big O helps engineers choose algorithms that will actually finish running in a reasonable amount of time on large datasets.
Are there practical tips for writing efficient code beyond just picking the right algorithm?
Yes, the source mentions a few key ones, especially relevant when working in languages like Python, which can be slow if you're not careful. Leverage optimized libraries, vectorization. As we discussed, use libraries like NumPy or Pandas. They are highly optimized, often using underlying C or Fortran code, to perform operations on entire arrays or matrices, vectors, at once. Avoid writing explicit Python for loops to iterate over large datasets whenever possible. Use the library's built-in vectorized operations, like adding 2 arrays element-wise with a single plus sign instead. This is often orders of magnitude faster. Use appropriate data structures. Python offers different ways to store collections of items, lists, sets, dictionaries. Choose the right one for the job. For example, checking if an item exists within a large collection is much faster using a set than searching through a list, if the order of elements doesn't matter. Profile your code. If your code is running slowly, don't just guess where the bottleneck is. Use profiling tools to identify exactly which parts of your code are taking the most time, and then focus your optimization efforts there. Prefer well-tested libraries. Again, stick to popular, well-maintained libraries like scikit-learn, TensorFlow, PyTorch for the core ML algorithms. They've been heavily optimized by experts. Don't reinvent the wheel unless you have a very good reason. Prefer well-tested libraries, hashtag, outro.
Wow, what an absolutely fascinating journey through the world of machine learning, starting right from the term's surprising origins.
It really covers a lot of ground, doesn't it?
It does. We've gone from understanding how machines learn in different ways, supervised, unsupervised reinforcement, to digging into specific algorithms like SVMs finding those margins, or decision trees acting like flowcharts. We saw how they actually learn using gradient descent, and how engineers make it practical with libraries.
And then navigating the real-world challenges. Crafting features, choosing algorithms, evaluating performance carefully, tuning those hyperparameters.
Right. And finally, getting a glimpse into the power of deep learning with CNNs and RNNs and all those other cutting-edge ideas like zero-shot learning or self-supervision.
Our deep insight dialogue today, really guided by the clear explanations in the 100-page machine learning book, hopefully gave you a solid, intuitive grasp of this field that can often feel pretty intimidating or opaque.
Yeah, the focus was definitely on the what and the why, trying to equip you with that foundational understanding without drowning you in mathematical formulas.
Exactly, making it accessible.
And it's so clear this isn't a field that's standing still, is it? The book itself highlights that constant evolution, new techniques emerging all the time, solving problems like that vanishing gradient that used to hold things back.
Absolutely. And the book's own model being continuously updated through its companion wiki kind of mirrors that. The author notes it's like a good wine, it keeps getting better after you buy it.
Ah, I like that.
It reflects the dynamic nature of machine learning itself, always improving, always adapting.
So as you, our listener, move forward with these insights, maybe keep in mind that quote from the statistician George Box, which the book highlights: all models are wrong, but some are useful.
That's such a crucial perspective to maintain.
Yeah, these machine learning models, they aren't perfect crystal balls capturing objective truth. They are powerful tools, approximations of reality based on the data they've seen, designed to help us find patterns, make predictions, and automate tasks. They are incredibly useful.
Which leads us to a final thought, maybe something for you to mull over. In a world that's increasingly shaped by these useful but imperfect models, what happens as they learn more and more about us and our world from the data we generate?
What new ethical questions arise? What practical considerations about fairness, bias, transparency, and accountability do we need to grapple with as these learning machines become more integrated into our lives?
And perhaps most importantly, how can your informed perspective, now grounded in a better understanding of how these systems actually work, contribute to shaping their development and deployment responsibly?
That's definitely something to think about. Thank you so much for joining us for this Deep Insight dialogue. We genuinely hope you're leaving feeling a bit more well-informed and maybe even a lot more curious.
Indeed. Until next time, keep learning, keep questioning, and keep exploring the fascinating world of knowledge.